Yep. First of all, welcome everyone. Thank you for coming. Today I'm going to be giving you an overview on what I think is the coolest and amongst the most important applied artificial intelligence problems of our generation, which is self-driving cars. Just some admin before we begin. I'm going to be answering the questions that you guys have at the end of the talk. So you're perfectly welcome to send questions into the Teams chat throughout my talk, and I'll just see and answer them after I finish. Also, there are some topics I cover through here where I've got like further reading links, and I've compiled them all into one one list in the document, and I'll get that sent into this channel after the talk is over. That's if you find something in here interesting and you want to read more about it. So I'll get started with why should you care about self-driving cars? Firstly, let's go over where we can actually make use of self-driving technology. The most obvious implementation is in our own personal vehicles, where we could go on our daily commutes without needing to control them. You could have fleets of robotic taxis that you could request on demand. So imagine a service like Uber or Lyft, but without human drivers. A use you might initially not have thought of was trucking, which is really useful for last mile deliveries and for transporting cargo. So now we know where we can use self-driving cars. I'm going to go through what I think are the three main reasons we'd want robots driving our cars in the first place. The main one for us is having the experience of taking the focus off of the road and doing something else. Right now, the average UK driver spends around 4 years of their life in a car. So we might be able to let us get back a lot of that wasted time spent driving and be productive or relax in that time spent in transportation. Although the convenience of self-driving cars is great, by far the most important reason to put time, effort, and money into autonomous vehicles is road safety. In the time that I finished reading out this sentence, someone in the world has died in a car crash. If we were able to bring fully autonomous cars to our roads, we could reduce road accidents more than seatbelts and airbags combined. In fact, systems that are already out there now are already statistically safer than humans at driving. The last benefit is efficiency. So, because of the increased efficiency of autonomous vehicles, you end up spending less time in traffic, which reduces your overall commute times. And it ends up with you spending less time on the roads. But we only really get the significant efficiency benefits where you have entire areas that are mostly used by self driving cars. In the early stages of adoption, like where we're at now, we have self-driving cars driving alongside human drivers, which doesn't really help efficiency that much. So the main reasons at the moment are convenience and safety. Um, let's go through some definitions. What actually is a self-driving car? So I've made a really small glossary of terms that tend to be used interchangeably, but they do have minute differences in their meaning. The first pair is self-driving and driverless. So a self-driving car is one that has an autopilot system and that can operate a vehicle, but the human driver can always take back control. On the other hand, a driverless car is a lot more advanced. It also has an autopilot system, but human physically can't take control. Imagine stepping into a car that has no steering wheel or pedals. That's driverless. The second pair of terms is automated and autonomous. So an automated car is operated by a machine and it can follow instructions, but they need humans to be there to take over if needs be. An autonomous car could act independently and make decisions for itself, like following a route or switching lanes or even overtaking another car. We aren't even close to having something properly autonomous yet. Um, so even though these words have differences in meaning, lots of people, even at big companies in the industry, seem to call automated cars autonomous despite them really only being automated. I'm lazy as well, so I'm just going to refer to both of them as autonomous vehicles. Also, AV is an abbreviation for autonomous vehicle. So let's define what we mean by self-driving. I literally ripped this off of the first line from the Wikipedia page for self-driving car. An AV is capable of traveling across an environment safely with little to no human input. Let's look more closely at what it means by little to no human input. These are the autonomous driving levels by the Society of Automotive Engineers. And essentially, these qualify the complexity of different autonomous driving systems. They go from level 0 to level 5, and the higher the level, the greater the autonomy. There are very clear differences between levels 0, 1, and 2. Level 0 isn't shown on this graphic, but it represents no autonomy, so no assistance in any aspect of the driving. Level 1 is where the car takes over either steering, so that's lateral control, or acceleration and deceleration, where it's a longitudinal control. You go level up to level 2, and that's where the car takes over both. Level 3, 4, and 5 are essentially just level 2 systems that are good enough, that they're safe enough to where the driver doesn't have to pay as much attention. These are pretty vague definitions for the capability of a autonomous driving system. So let's more specifically define the capability of an autonomous vehicle. Here's an excerpt from a blog post I read some time back on the safety of self-driving cars. They talk about this thing called the ODD, or the operational design domain of a driving system. The purpose of the ODD is to provide a more rigorous specification for the scenarios in which an autonomous vehicle can drive. And so the larger or wider the ODD is, generally speaking, the system is more capable since it's able to perform in a wider range of driving scenarios. One other point to make is that the ODD of a system is always finite, because in reality, there's an infinite number of possibilities that you could encounter while driving. And for the same reason, trying to aim to make a autonomous vehicle that never crashes is a ridiculous goal. You could build the world's best robotic driver, but if a wheel falls off, then what do you do? There are lots of things out of control from the people that write software for autonomous vehicles. Let's look at where autonomous vehicles are right now. Unsurprisingly, the vast majority of the cars on the road worldwide today are at level 0 autonomy. Level 1 vehicles have actually been around for many years now. Lots of relatively new cars by traditional automakers are level 1. So you might find, even in your parents' car, you'll see features like automatic emergency braking, AEB, adaptive cruise control, ACC, and lane keeping assist. Note that each of these automation features control one particular aspect of driving at a time, but they don't form one full system that you could say actually fully drives the car. Moving up to the level 2 systems, this is the point where I'd consider the systems to be able to operate a vehicle autonomously. Level 2 systems are road legal in the vast majority of countries today. The biggest level 2 system by users is Tesla's Autopilot. The Autopilot itself is mostly intended to work on motorways at the moment, but it can also run on some other roads too, with their new product called full self-driving. But that's still a bit of a lie, because it's not really self-driving, but it's far more capable. So far, they've driven over 3 billion miles on roads in the world, making it the biggest fleet of autonomous vehicles that are out there right now. Tesla Autopilot is already significantly safer than manual drivers when you consider the number of miles driven before an injury or fatality occurs. The second biggest fleet of level 2 systems is by Comet AI. It's called OpenPilot. It's open source actually on GitHub. It's far cheaper than Autopilot because, as you can see in the picture there, it's a standalone module that you buy and then you plug into your vehicle, assuming it's compatible. It's almost like a dash cam that plugs into your car and that can also drive it. Some companies have decided that the best approach to autonomous vehicles is to go straight for gold and develop systems for these higher levels of autonomy, 3, 4, and 5. The two main ones right now are by Google, who's been working on this for tens of years now. The company is actually called Waymo. They offer a robotaxi service that's level 4, and Cruise is the other one, and they're trying to go for a driverless vehicle that's also level 4. The one note to make about these level 3, 4, and 5 systems is that they've either been cleared to operate in very confined regions with a remote human supervising it, or they still have a human behind the wheel. So, for example, Waymo's Waymo 1 taxis, they only run in Phoenix, Arizona, in a restricted geographical area. Okay. The only real quantitative measure we have right now to measure how good an autonomous driving system is to consider the miles between disengagement. This is essentially the number of miles on average between when you turn an autonomous driving system on, and when the human has to take control back. It's a vaguely a mean time between failure kind of measure. At the bottom, I've got a vaguely logarithmic scale for miles per disengagement, and let's stick some things on here. So firstly, we talked about earlier with the the ODD stuff. We've established never crashing is impossible. Right now, the traditional automakers are at around 1 mile per disengagement with their level 1 systems, and moving up 10x, most of the big self-driving startups are at around the 10 mile mark with their level 2 systems. The only company that's 100 times better than that is Google with their Waymo 1 level 4 system, but you've got to remember that's only in Phoenix, and all the previous ones can drive on any road. What's at 100,000 miles per disengagement? Humans. That is the level of risk we're willing to accept with driving today, and now that gives us a sort of a bar to beat with trying to create a superhuman driving system. So now, now we know that what's available at the moment, but let's go right back to the basics. How do you create an autonomous vehicle? Let's start by considering the problem we're trying to solve first. The goal of autonomous vehicles is to create a driving system that can control the steering and the acceleration/deceleration as well as possible in the widest range of scenarios. To do this, we need to be able to create a machine that's able to control a vehicle predictably and drive like a human. This is assuming that we want our system to drive amongst human drivers like we would today. So creating a real autonomous vehicle is a huge technological challenge because of the scenarios in which the systems operate. Autonomous vehicles operate in complex and dynamic environments. So to do that, you need to model all the objects that are around you. And sometimes you have a matter of milliseconds to make a life or death decision. So these systems need to be able to keep up. To make informed control decisions, you need to accurately perceive your environment. But most of the ways we have to get computers to perceive objects in their environment now are still far inferior to how humans perceive and reason with our eyes and brains. Also, the environments that the autonomous vehicle might drive in could have varying conditions. So this could include different visibilities or traffic or shadows and a couple other on the list up there. Let's break down the driving problem. I'm going to put it into 3 stages where each of them builds on the previous. So the first one is the static driving problem. This is where you drive being the only vehicle on the road. A static driving problem, this would let you drive on a looped track. So if you want to go go-karting or, I don't know, drive a Formula 1 car where you're the only car on the track, the static driving problem is what you have to solve. To solve this, the primary sub-problem to solve is to create a good lane keeping system. And there's not much else to that static driving problem. Moving up to the dynamic driving problem, this is all the components of the static driving problem, so that's lane keeping, as well as considering all the objects that are not static and planning appropriate actions in real time. So the objects that might move over time, you need to predict what the objects are going to do and then plan your motion accordingly. A dynamic driving system would let you drive in urban environments. So this would include detection and predicting the trajectory of other what we call agents in the scene, including pedestrians, vehicles, and cyclists. You also need to detect road signs and traffic lights to be able to follow road rules. Yep. And then the last part of the problem is the counterfactual driving problem. And in the dynamic problem, you adjust what you do, what the vehicle does, based on what the other objects in the environment are doing. Like, for example, if a pedestrian is crossing the road in front of the vehicle, you try to first detect the pedestrian, predict which way they're going to move, and if you see that they're going to move into the path of the car, you'd write a bit in your algorithm that says to apply the brakes if that case is detected. But solving the counterfactual problem is where you include the autonomous vehicle's influence on other people. So to give an example of this, when you're going up on a slip road to join a motorway, your car being there tends to affect the motion of the cars that are on the left-hand lane of the motorway. like they tend to slow down a bit to let cars join the motorway. Somehow you need to put the expectation of other cars or pedestrians or whatever it might be changing what they do depending on what we do. We need to put that into our algorithms. And this is one of the most difficult unsolved problems in the entire field of robotics, not just in self-driving vehicles. Before we come on to how we actually design autonomous vehicle systems and algorithms, I'm just going to go over some relevant theory for self-driving cars. The first thing to cover is artificial intelligence, or AI, which you've most likely heard of by this point. AI is technology that solves problems autonomously by simulating human intelligence. This is really broad and it encompasses a lot of things, but it's common to talk about autonomous driving systems as being a kind of artificial intelligence, because a driving system makes control decisions by trying to reason about the world like a human. We'd want our autonomous system to follow the same logic as a human would in any scenario, like, oh, I detect that there's another vehicle coming up in front of me, let me apply the brakes and begin to slow down. Where we allow machines to gain a high-level understanding of an environment, that's called computer vision. Computer vision is a really broad field that encompasses lots of different techniques. This could include detecting objects, so that could be vehicles, cyclists, traffic signs, traffic lights, or road markings. Or it could be 3D pose estimation, which this is where you try to model the pose that a human is in. This is useful for self-driving cars because we can try to model the pose of pedestrians, which would help us try to figure out the help us try to predict the motion of a pedestrian. And also SLAM, which is very relevant to self-driving cars. This stands for simultaneous mapping and localizations, where you use maps and sensors to try to figure out where you are relative to other objects using images. These techniques tend to involve analysis of data that comes in from sensors like cameras, as well as point cloud data from LiDAR, which I'll come on to in a moment. Okay. This is a really quick and dirty demo I put together for computer vision. This is a lane line detector that I made in Python. On the left, you can see the video I passed in. And on the right, you can see the output where I've drawn pink lines to represent what my program estimates to be the lane lines. It works by using some image filters, an edge detection algorithm, and some simple linear regression that I wrote from scratch. Of course, in reality, for those of you that know what linear regression is, this system would fail as soon as there was a turn in the road because I haven't given it the capability to try and detect a curved road. This is more of a very, very basic introductory thing you can do with computer vision. It can get way more powerful than that, and all the code is up on my GitHub there. This is a second example that I've passed into my lane detector, and this one's literally off YouTube from someone's dashcam video. And there's a specific reason why I chose this video in particular. Do you remember earlier when I said perception is a difficult problem for self-driving cars because you can have varying lighting conditions? This is a perfect example of that. So if you look at the shadows being cast from the left side, this causes my algorithm to skew. It thinks my left lane line is more slanted than it actually is because of the shadows being cast on the road. Of course, this is because my algorithm's super primitive. I could try and improve it to account for shadows, but my point is that things like shadows and other visibility problems add so much more layers of difficulty to the perception problem. Okay, this is entirely unrelated to self-driving cars, but while we're on computer vision, this is another quick thing I did with it. It tracks the tip of your finger and lets you draw something. It's useless, but it was fun to make. Anyways, back to the rest of the theory. Okay, machine learning, you've also probably heard of this. It's an application of AI that lets systems to improve from experience or data without being explicitly programmed how to execute a task. Machine learning algorithms are commonly categorized into three types. The first type is the most common, and this is supervised learning. This is where you try to develop a predictive model based on a data set that contains known inputs and outputs. Then we have unsupervised learning, which is where you try to get a system to recognize patterns in data that's unlabeled. And so you're trying to get a computer to infer structure in some data. The last one is probably the most interesting one. This is reinforcement learning, and reinforcement learning is a method where you get an AI to explore and interact with the environment and use that to learn. Machine learning algorithms often utilize artificial neural networks, which is it's a data structure that's inspired by the structure of biological neurons, like the ones in our human brains. I'm not going to get into the weeds on these, but if you're interested and want to understand the maths behind these, 3 Blue 1 Brown has a really good introductory video series on neural networks. I'm going to link those in my further reading notes. So neural networks are essentially composed of nodes that are connected to other nodes with connections that have different strengths that we call weights. Feed-forward neural networks, like the one in the picture, are structured into distinct layers. They begin with an input layer and they terminate in an output layer. You feed input values into the first layer, and then they are successively multiplied by the weights through each layer, and eventually in the output layer, they produce a value that represents some signal. Initially, these weights are set to totally random numbers, so as expected, we get totally random and meaningless outputs. Then, how do we get this neural network to learn, like in the name machine learning? For it to learn, it follows a process called backpropagation. So backpropagation is, well, I've put it into a 3-step process here. So first, this is for supervised learning, where we know an input value and we know the correct output value. We take an input value and we run that feed-forward operation through the network to compute an output prediction value. Then the guess that the network has made, we compare that to the answer that we know in our data set, and then we compare those to create a error value. And then using an algorithm called backpropagation, which the results you can see in the top right there, the weights, so the connections between the nodes, are adjusted depending on what the error is and how big it is. It involves some maths with gradient descent and partial derivatives. I wish I could go into it further, but that would be a whole other lecture to explain, so I'll leave it there. If you're interested, the 3 Blue 1 Brown series or lecture notes from a Stanford course on machine learning, I'm going to put both of those in the further reading notes. And so essentially, you run this backpropagation algorithm many times, and these weights keep getting adjusted, and the idea is eventually the network should give us meaningful outputs. So for example, for self-driving cars, you might feed it sensor data and then get it to predict a steering angle or a throttle value for us. And initially the steering angles and throttle values are going to be random, but as you get it to run through more learning cycles, it should give us meaningful outputs based on the sensor data as to what steering angle to choose. Okay. The next bit of theory is deep learning. This is pretty straightforward. It's just machine learning, so what I've just described, but with extremely large neural networks that have lots and lots of nodes and lots of connections. Using networks with more nodes lets the models have a much greater capacity to learn things, and they're really useful for when you're working with data like audio or images from a video stream, like we would in an autonomous vehicle. The problem with using a bigger network, though, is that first you need more computational power to train it, and you also need more data to get it to train well compared to a much smaller network. Okay. And convolutional neural networks, they're a class of deep feed-forward neural networks that are really good specifically at analyzing images. They learn using the same backpropagation method that I described before, but they utilize kernels, and the kernels essentially let the network extract features from images. You use a kernel to do an operation called a convolution. There's a visualization of that in the video on the right, and it's some matrix maths that I'd love to go into as well, but I won't for brevity. Okay. So now we're going to go through some history of self-driving cars. Probably the earliest self-driving system that you can find is the ALV, Autonomous Land Vehicle, which was by Matthew Turk back in 1988. The ALV used a single color camera, and it used a very simple algorithm to try and segment the video feed into what was the road and what was not the road by its color. And it was able to, well, so use that data, what was the road and what's not the road, into a very simple mathematical algorithm to calculate a steering angle. It was able to drive at a maximum speed of 2 miles an hour. But the problem with using an algorithm like that is when you have a road that's of similar color to the rest of the picture, the whole system fails because it tries to figure out what the road is based on color. So in these examples, it wouldn't do very well. Okay, moving forward a couple of years, the next big milestone was probably the system called Alvin by Dean Pomelo at Carnegie Mellon in 1995. Alvin stands for ALV, Autonomous Land Vehicle, in a neural network. He used, for the sensor, one camera, just like the ALV from before. But for the algorithm, instead of using a simple mathematical one, he used a relatively small neural network with 1,292 total nodes in 3 layers. He passed images from the camera into the network, and it would produce a steering angle. And over time, he trained this to try and produce the good steering angles for driving. And this system was able to drive at a top speed of 70 miles an hour, which is a significant improvement from any other system at the time. And in fact, the system, the neural network was trained so well that it was able to make it across the whole of America, running 98% autonomously in an event called No Hands Across America. Let's go to a more modern implementation. This one is by NVIDIA, and it's called Dave 2. For perception, it uses one camera like the previous two, but for the algorithm, it uses a very, very deep convolutional neural network with lots of millions of parameters. This was only possible to use because of how powerful computers had become in the last couple of decades. And this took an entire video feed from a camera and output steering angle and throttle values from the neural network. And the network was capable enough to drive in urban areas, including, amongst other cars and in parking lots without crashing. The success of Dave 2 is mostly because of two things. Firstly, because the network that they used is so deep, so huge. And second, because they gave the network a large and diverse set of human driving data to learn from. So let's get into how you actually design an autonomous vehicle. This is a screenshot from a Robotics 101 class, and this structure is no different for our self-driving car systems. Perception and localization is to do with seeing what's around you and figuring out where you are in relation to other things. Planning is where you use algorithms to evaluate a trajectory for the vehicle to go based on road rules or other data you might have. And control is where you use that plan that the planner has produced and you translate that into smooth, comfortable steering, acceleration, and braking. You can actually see very good parallels between how humans do this and how we'd want a robot to do this. So localization and perception, that's our eyes essentially. The planner is our brain, and the controls is our muscles. So it's like GCSE biology kind of stuff. So let's start with perception systems. Perception in an autonomous vehicle is essentially just some array of sensors. I'm going to go through some of the most popular ones now. By far the most popular sensor that's used for self-driving right now is cameras. Using a camera emulates really well how humans perceive environments as well, because if you think about it, our eyes are essentially biological cameras. The advantages of using cameras is that they give you data with a really high resolution. They give you data about color, which lets us infer lots of information like the color of a traffic light. And they're also cheap and ubiquitous compared to a lot of the other available options for sensors. The disadvantages from using camera is that they give us 2D image data. And because we live in a 3D world, we don't get any explicit information about depth or distance from an image. But using computer vision algorithms like the SLAM one I talked about in the CV section, that helps solve that. And also cameras can be affected by harsh conditions and bad lighting. If you had a driving system that used only cameras, your entire system would fail as soon as you tried to drive when the sun went down. And I used cameras for my own project that I'm going to demo at the end. The next most popular one is LiDAR, which stands for Light Detection and Ranging. It essentially illuminates objects using a laser and then measures the time of reflection with a sensor. And if you put this on the top of a vehicle, you can get a 3D view of all of the objects and how far away they are from the vehicle. This produces a really high resolution map, which consists of essentially just a vast set of points in virtual 3D space, and that's why it's called point clouds of the surrounding environment. The advantages of using LiDAR is that it gives us really, really accurate depth and distance information, and it's by far the most accurate ranging sensor that's available at the moment. Also, the point clouds that we get from LiDAR are of extremely high resolution, and because they're put on top of the car and they rotate very quickly, we get 360 degrees of visibility. And the visibility of LiDAR sensors isn't affected by adverse lighting conditions because it uses lasers. And yeah, LiDAR sensors are very reliable. The problems with LiDAR sensors is that they're very, very expensive, but they are becoming slightly cheaper. And also these sensors, because it's a ranging sensor, it doesn't give us any color data. Some other sensors that we can use are radar and ultrasonic. So to start with radar, radar is similar to LiDAR. It's a ranging sensor, but it uses much longer wavelength radio waves instead of lasers. They're already quite common in cars now, and they're used for things like parking sensors. And well, the pros of them is that they're pretty cheap and they're not affected by extreme weather. The disadvantages of radar is that they give us really low resolution data. So radar is better used as sort of like a redundancy sensor, like a secondary sensor that helps us confirm things are there. And then ultrasonic sensors. These are ranging sensors, but they use sound waves instead of radio or laser waves. And so these are good because they're really inexpensive, and they're also not affected much by extreme weather. The problems with using ultrasonic sensors on cars is that they have a really short field of view. So if you're trying to detect cars that are in other lanes, it might not be that good for that. And it's also less accurate compared to like LiDAR. And probably the biggest problem is that when you're moving at fast speeds, because of the behavior of sound waves, the ultrasonic sensors don't really work well. Okay. So moving on to the next bit of our system, the planning part of our system. This is going to involve algorithms that make decisions and compute driving commands. The basic idea is to map data from our perception system, so this is cameras or LiDAR, or whatever it might be, to control signals, which would be a steering angle or a throttle or a braking value. The current approaches to self-driving are roughly categorized into two sets. The first is where you have a modular pipeline, and the second is what's called a monolithic end-to-end learning approaches. I'll start with a modular pipeline. This is the standard approach to autonomous driving in industry. It's called modular because essentially you break the driving problem down into loads of different modules, and then you try to solve each module independently. So they can be independently developed and tested. And for this approach, machine learning is less likely to be involved, and it's more likely to have loads of sensors stuck to the car and lots of computational power to process all of the data. You'll see this approach being used at places like Waymo or Cruise, where they're trying to jump straight to level 4. Tesla is sort of an anomaly because they use essentially a modular pipeline, but they do use machine learning, which is unique. The advantages of breaking the problem down like this is that because humans have designed them, because we haven't incorporated machine learning, it's easier for us to understand where they've gone wrong. And because we've broken them down into lots of different small problems, it's easy to develop them all simultaneously in parallel. Actually, it's funny. There's this guy at Google's Waymo that whose role is essentially him being the cone guy. His entire job, his salary is paid trying to detect traffic cones as best as possible. That's probably an extreme case of modularization, but Also, modular pipelines tend to be safer because they use more sensors, and because of that, you might be able to get to the higher levels 3, 4, and 5 quicker if you use this method. The problems with it is that because you're not using any machine learning, you have to define to the computer what things look like, what's called feature extraction. So, for example, you have to try and define what a car looks like, and you have to define what a pedestrian looks like and whatnot. And the problem with that is that humans trying to define how what something looks like to a computer isn't necessarily the optimal description of how a computer would comprehend it. And it's also not very generalizable, and it tends to only work in confined regions that have been mapped out really, really well. And it's also very, very expensive to do. So let's go to the complete other end of that, which is monolithic learning. These approaches are often called pixel to pedal because they're generic models, often based on neural networks that take in observations and map them to actions. They try to learn the entire driving task in one neural network. The two most popular methods to learn the network's weights are imitation learning and reinforcement learning. So let's start with imitation learning. It's also known as behavioral cloning, and that's because the basic premise of it is where you record data from a teacher, like a human, and you show it to the network, and yeah, so you show the recorded data to the network until it learns to drive like the teacher. So it's cloning the behavior of the teacher. You need lots of data to do this, and you also need a large network for it to do it well. The advantages of imitation learning is that it trains relatively quickly, and you can get up to a relatively good accuracy in little time. Also, these imitation learning algorithms are simple. They use the backpropagation method I discussed earlier from supervised learning, because imitation learning is essentially a type of supervised learning. You have a data set and you're training a neural network off of it. It also lets the neural network define feature extraction, and yeah, so it lets the network figure out what things look like by itself. So humans don't have to tell the network what, for example, a car looks like or a pedestrian looks like. It tries to extract and learn those features by itself. The problems with using this method is that because you're teaching the network how to drive from human data, it means the data is going to have errors because humans don't drive perfectly. So this means that the neural network is never going to be close to perfect. It also means that because we're teaching it from humans, fundamentally the agent fundamentally can't become superhuman, which is one of the long-term goals of the autonomous vehicle industry. This method is the one that I used for my project that I will also demo afterwards. Reinforcement learning is very new. In this, we let AI explore the world by making actions, by producing actions, and we try to get them to define to maximize their score on a reward function that we define. And well, the first thing is letting an AI explore the world driving a car is definitely not safe because it's going to make lots of mistakes at the beginning. But over time, these could genuinely learn some intuition over how to drive a car properly by itself. The advantage with this is that it has a much bigger potential than imitation learning, and so it might generalize better. It also doesn't require a data set, which avoids the human bias from the imitation learning from before, because it just interacts with the environment by itself. The problems with it is that it takes a very, very long time to train. It does loads and loads of rounds of trial and error before anything of significance is really learned. And probably the biggest problem with this is, and the reason why it hasn't been done yet, is how do you define a mathematical function for what constitutes as good driving? Because to drive is to essentially, the definition of driving is what humans do when they drive. How do you put that into something algorithmic that you can put a quantitative score on? The last section of the problem was control. Controlling the car is pretty simple. You have a drive-by-wire system where you can just send the vehicle electronic commands numerically for steering and throttle, and most of the controls aren't very complex. They're something like moving the steering wheel to the side a bit, or pressing on the throttle a bit, or pressing on the brake a bit. This part of the problem is actually really easy compared to other autonomous systems. Probably the hardest one I can think of is trying to hover a helicopter upside down, where the control model for a helicopter is way more complex than it is for a car. Because with a car, you're dealing with 3 degrees of freedom on flat roads, whereas when you're in the air, you're dealing with all 6. So on the right there, that's Stanford's autonomous helicopter from back in 2008, actually. Okay, I'm gonna go over some other ideas that I thought were interesting. Firstly, connected vehicles would be where autonomous vehicles can communicate with each other to plan out coordinated movement of the entire system. And this involves a whole class of algorithms that is in another area of open research. You'd also need huge amounts of infrastructure to handle the data. In fact, part of the reason why companies are pumping so much money into 5G isn't so that you can watch Netflix faster. It's so that communications could communicate with each other and maybe be autonomously in the future. And so there's two ways of doing this. You can have V2V, vehicle to vehicle, where you have a decentralized network of cars communicating with other cars. Or you could have V2I, vehicle to infrastructure, where you have a centralized network that's all controlled by the infrastructure that the vehicles are connecting to. It's actually been done already, and right now they're restricted to very specific use cases like ground transport at airports. In the far future, if we could get something working like this in a city, you could redesign the entire city. You could remove traffic lights at intersections because all the cars could move almost in harmony together. And the second one is the boring solution. This involves digging tunnels underground and having a car essentially transform itself into a mini train and get driven at high speeds underground. Elon Musk is planning this with the Boring Company in Los Angeles. I think this looks really cool, but very, very expensive and also a logistical nightmare trying to dig loads of tunnels underground. The last one is flying cars. We've all heard this one. I don't think this is feasible, but some companies are considering it, including Uber. So this could be a thing at some point. I don't know. I'm not very optimistic. Okay, that concludes all of the theory for autonomous vehicles. You can leave if you'd like. I'm going to do a demonstration of my project that I've mentioned a couple times before. So I hope you enjoyed the theory. Now I'm going to get on with the demo. So this project was my coursework for my A-level computer science, and the general premise was to build a autonomous driving system. And to give a brief overview of how I chose to design it, first of all, I built the system to work with a simulator, but it's possible to use it in an actual car. I just need to spend time trying to port it to do that. I also don't think that's legal. So for the perception portion of my system, like I said, I used one color camera that's on the virtual car in the simulator. And then for the planning algorithm, I used imitation learning on a deep convolutional neural network that was very similar to NVIDIA's Dave 2 neural network. You can see the architecture of that on the right. It has 27 million weights. So yeah, that's the design of my project. Let me get on with the demo now. So the simulator that I chose to use was this one. It's from a nanodegree by Udacity. Okay, it gives me two modes. It gives me training mode and autonomous mode. And if you remember with imitation learning, you have to record a data set to train your neural network off of. So it gives me two tracks. I'm gonna choose this one and enter training mode. Then if I hit the record button, it gives me the option to record a data set. So I'm gonna put it into this folder called demo drive here. If I select it and then hit record, I can begin driving. This is a one-lane track with pretty consistent lighting, and the turns are very gradual. So this is like probably the easiest kind of track you could build a self-driving car for. This is good. This is a good starting point. I'm not going to go the whole way around. I'm just going to do a very short data set. All right, stop there. Now it's going to capture and save to the folder I chose on disk. Actually, you can see here, this is the folder I have for it. It has a driving log, which contains, it essentially took 3 images. So this is the left camera, the right camera, and the left camera, the center camera, and the right camera. So it took 3 images, and then this is the steering angle, and then this is the throttle, this is the braking, and this is the speed. So it's recorded that into a big table. And for the images, it's just given links to the images on on disk. So if I show you one of the images, this is, for example, this is one from the center camera. Very low resolution, but that's an example of one of the images from the dataset. Now I've recorded my dataset, I am going to open up this application I made that I call the trainer. It's a web app where you can easily train my system on the datasets you record. So I have two sections. I have the datasets and I have the models. So here's the datasets I have. I'm going to add the demo dataset I just recorded. I recorded this on track 1, and the comment I just used for myself really, but like I say, used mouse, stayed in the middle, maybe like half the track. Okay, now I've added the dataset, and then I can edit and remove it. But to create a model of a neural network trained from the dataset, I enter the training here on the dataset I've chosen. Now it gives me the option to choose all of the different parameters for training on my neural network. These are defaults that I found through essentially just trial and error. These take normally like 20 minutes to do on my computer anyways. I'm going to reduce it so we don't have to be waiting for 20 minutes for it to train. Normally you'd have maybe, so remember I talked about backpropagation, you want to have loads and loads and loads of training rounds. Normally I'd have a couple tens of thousands of training rounds. Here I'm going to reduce it to 15 in total. And if I begin training, it will run those 15 training rounds on my neural network from the dataset I just recorded and spit out a model that I can drive from. Okay, this is the one thing I didn't want to happen with a live demo. Okay, it looks like it's created the model, but it also produced a graph that was meant to show up on the web page, but yeah, here it is. This is the training graph for that model I just trained, and so on the x-axis here is the essentially the training round, and on the y-axis is the error. So if you remember, I talked about how we have the known value. So for me, that was the steering angle I had recorded in my dataset, and then I had the value that the network would make as a guess, and then I'd compare them and produce the error value. And this is how the error value changed over time. So you can see it gradually reduced, and this is very few, so it's still quite big, but over time it would become better. So now that I have created that model, you can see it here, the demo drive model that I've created. I'm going to boot the simulator back up and boot the other application I made, which is called the driver, which is a user interface to easily load up and drive from models. So I'm going to load up the model I just made. That's in here, demo drive. Now I'm going to open it. My network only spits out the steering angle. I haven't trained it to predict throttle values. So for the speed, I've actually got a really simple algorithm for that. I'm going to stick it on maximum and go into autonomous mode on the track I trained it on. And if I hit start, it will open up this monitor and then begin, in theory, begin driving. There you go. Okay, it's gone off the track immediately. And the reason it's done that is because I only had 15 training rounds. So the neural network is essentially spitting out meaningless rubbish at the moment because I haven't trained it enough. Let me load up a model that I've pre-trained before this on many more laps of dataset recording and also tens of thousands of training cycles. So this one here. And if I start, oh, that's the wrong track. That one there, okay. So if I start driving, you can see that this train model is controlling the car around the track, and that was maybe 20 minutes of training over 5 laps of this particular track. And my hands are off the keyboard. I'm not controlling it. You can see it says mode autonomous. That is my system driving the vehicle around the track. And this one will be able to make it around a full lap around the track because it's been trained it's been trained enough. So whilst that's driving, actually, I want to run through the algorithm I used for calculating the throttle. So um, let's bring this over here. So this is the algorithm I use for calculating my throttle value. It's throttle equals 1 over the speed divided by the speed limit. And the reason I chose this is because 1 second. No, so the reason I chose to do this is because, let me just draw quickly. If you're going uphill, your speed is gonna decrease. So your speed will be less than the speed limit, and that means that speed um, divided by speed limit is going to be less than 1. And so that means that the throttle is going to be is going to increase. It's going to get close to 1. Bear in mind the throttle goes from I think -1 to 1, where -1 is full brake and 1 is full throttle. So if you have your speed becoming a lot less than the speed limit, this fraction is going to become less than 1, and then your throttle is going to increase to compensate for that. So that works for going uphill. Obviously, that doesn't matter for this track because it's entirely flat. And also, then if you had a downhill section of the track, then your speed would increase because you're going down. So that means your speed will become greater than your speed limit, and this fraction will become greater than 1, and so that means this whole expression will become less than 0, and therefore it will begin braking to try and remain around the speed limit. So that's the relatively simple mathematical algorithm I used for throttle. So now it's made it around 1.5 laps around this track, and this isn't even the full extent of the system's capabilities. Let me pull up this track. Let me just drive on it for a moment. You'll see this track is a lot more complicated. It has inclines, and it has much more sharp turns, and it also has shadows, which if you go back to the visibility stuff I talked about earlier, having shadows on your track makes it a lot harder for the algorithm to discern what where the lane lines are and what to drive and whatnot. So this is a more difficult track, and let me show you a model that I've already pre-trained for this track, a different model. Okay, theory it should start driving. There we go. Okay. I've got this to drive slower than I did on the previous track because if you drive too quickly, then it doesn't give the system enough time to react. So I've deliberately slowed it down and set the speed limit to be lower. And you'll see that this track also has 2 lanes, whereas the first track only had 1. So that means that and the data set that I trained this model on, I drove remaining in the right hand lane. Essentially what I was testing here is to see if my system was able to learn to incorporate lane lines into the features it extracted, and it looks like it has because it's now remaining in the right hand lane. Obviously, for this particular scenario, it doesn't really matter because there's no cars coming on the oncoming lane. But the fact that the system has learned to do that is quite impressive. The fact that it can remain in one lane and detect where the lane lines are and adjust accordingly. And you'll actually see as we go downhill here, the red lights pop up. My very, very simple throttle calculation algorithm is doing its job right, and you'll see the speed increases over the 15 mile hour speed limit I've set, and then it comes down quickly. So this is the extent. This is the best my system can do in this particular simulator. That doesn't mean that the system couldn't do any better. It's just I haven't tested it on. This is the hardest track that's available to me in this particular simulator. So yeah, that just about concludes my my demo for my NEA project. Yeah, I think I'm ready to take questions now. If you'd like. I don't think they can unmute. So if you just drop them in text chat, that would work. Yeah, perfectly fine. So question is, do I think level 5 autonomy would be first reached using a monolithic or modular approach, or a modular plus ML? Um, okay, I think a modular approach will be able to reach it first, but it will only be able to reach level 5 in a restricted area. So like what Waymo's doing in that very very confined geographical region, they've mapped out that place really really well, and they've given their cars loads of sensors to work with, and then they sort of handcraft these algorithms to try and figure out what road signs and all the other objects in the scene. I think that's going to be the first thing to reach level 5, but I don't think that's necessarily sustainable. Yeah. What can my car actually see in this example? Oh, sorry, I should explain better. There are 3 virtual cameras on the front of the car, one on the left, one on the center, and one on the right. When at the moment when it's driving, it can only see a video feed from the center camera. So it's seeing a series of images from the center camera, like the one I showed you in the data set. It's seeing that, predicting a steering angle. And that's it. It's camera. This entire system is camera only. There's no other sensors involved. Do I think my model would work in real life if I had the resources? Absolutely, and that's one thing I really wanted to test, but I don't have the resources to. The entire screen, lasers coming from each side. No. So it's literally just a camera on the front of the car. I can pull up the image if that would make it easy to see. This is just one from a dataset I recorded on this. Actually, the dataset that this model is trained off of. There we go. This is essentially what the model is trying to predict the steering angle from. That's all the data it has access to. Okay. How long do I think it is be until self-driving is a societal norm, at least in the Western countries? I think it will. Self-driving will become a norm in Western countries first, and even then, not in metropolitan areas. I think it will happen in much more rural, quieter areas that have well laid out road networks. But in the long term, I honestly don't know enough to make a feasible prediction over when the majority of the cars on the road will be self-driving cars in Reading or something. It's a long way away. I think Elon Musk is making big predictions with that. A lot of other people are making big predictions. I'm not so optimistic. I think it's a much harder problem than what some people make it out to be. Aren't there also 3D cameras that are available in the market? If there are, why aren't these used? Okay, 3D cameras. Okay, honestly, let me Google this. Okay, if 3D camera is what I'm thinking of, where you essentially use 2 cameras and then the difference between their views to try and estimate distance, like human eyes do with the left and right, with their left and right eyes to try and estimate distance. If there are 3D cameras that work well, okay. Yeah, it's essentially the same thing. Yeah. They're already being used. They're already being used. The idea is to have multiple cameras and then use the difference in their perspective to estimate the distance of something in the scene, and it gives you more information than just one camera. What do I think the biggest limitation of AV development is? Ethics or technical limitations? Both, but I think ethics is an inflated problem. So I think we've all heard of the trolley problem. You know, or like a rendition of the trolley problem that's related to self-driving cars, where if you're going at some speed and you don't have enough time to stop, and the choice is between hitting someone you detect as being a child and someone you detect as being an old woman or a pregnant lady or whatever, that decision, I think that's an unrealistic problem to give, because if you had a system, you wouldn't get yourself into this scenario at any point in time. So I think ethics is still a problem, and the legalities are difficult, but I think at the moment the technical limitations are what's stopping us from reaching high levels of autonomy. Do I consider an autonomous vehicle a possibility without any sort of V2X, V2E being implemented? And do I think such technology would help the development of AV? Most autonomous vehicles that are out there today are not connected at all. Most vehicles aren't connected at all. So I absolutely think autonomous vehicles are possible to make without having any connection to other vehicles or agents in the scene or to some central infrastructure. I think that only becomes feasible and we'll only see significant improvements in our driving ecosystems if we have in areas where almost all the cars on the road are autonomous vehicles, because then you could connect them all to an infrastructure, and you'd have a system that knows where all the vehicles are, and then use a set of algorithms to determine what's the most efficient way of getting all of them to move. So yeah, absolutely, I think it's possible, but I think we'll only see big leaps in V2X happening once we have most of the cars on the roads being autonomous. Do I think end-to-end machine learning is possible for self-driving cars? The system that you're seeing on the screen is end-to-end machine learning. It's absolutely possible. NVIDIA did it. Loads of other companies have done it. Do I think it's a good idea for long-term economy? Long-term autonomy? Probably not. I don't think it's necessarily the best way of going about it. I think the best, generally the best way of doing it is to have some middle ground between modularity, breaking down the problem, and using machine learning. So you use machine learning, but don't use one model to predict the whole system. I chose to use end-to-end because it's simpler, really. What do I think about potential cybercrime related to AVs like hacking of cars? That's a problem. There are some good DEF CON talks actually on hacking autonomous cars remotely, and I think it becomes even bigger of a problem when we talk about V2V and V2I, because you have control commands being sent over a network, whereas now most of the control commands are being done locally. I mean locally to the car. So there's a computer on the car, and it takes inputs from the sensors, and it produces a steering angle. So to hack that, you have to gain access to the computer in the car, and then modify that to change whatever output values you're producing. Whereas if you have V2X, where you have vehicles communicating with each other, either directly or through some centralized infrastructure, then if you have someone gain access to that infrastructure, find vulnerabilities, that becomes a much bigger problem. There are way more attack surfaces for when you have connected networks of cars. Have there been any implementations of this in trains or trams or vehicles on a set track, and would this be easier? Absolutely. If you guys have ever been to, well, probably at Heathrow, they have those like mini train pod things that take you from terminals to car parks. Those are fully autonomous. Like they're managed by a central. Obviously, they're supervised by humans, but that entire system is entirely like hands off. So yeah, trains or trams, that's absolutely possible, and I think it's far easier than doing it in a vehicle, because you have set paths to go on. Whereas with cars, it's a road, but you have so many other options to go through. So yeah, they have implementations, and it would be a lot easier than doing it with a car. Yeah, Kieran, that's right. The DLR in London also operates with no driver, but the system is different from the one I talked about in Heathrow with the pods, because it still has humans setting routes for it. The Heathrow pods, people get into them and then they set routes themselves. So the DLR is a bit less hands off than the Heathrow pods, but yeah, same principle. Great. Any other questions? Wouldn't the modular ML approach eventually trump the monolithic approach, as the machine has a more authentic understanding of input data and features? What do you mean by authentic understanding of input data and features? Because modular ML means you have loads of concurrent subsystems trying to detect different things at the same time. And this isn't necessarily as efficient as trying to segment the scene into a known set of objects. So to put that in English, if you have a modular ML approach, you essentially have one little thing trying to figure out where the cars are, another little thing trying to figure out where the people are, another thing trying to figure out what the traffic lights are, all running in parallel at the same time. If you have a monolithic approach, you have one system that's looking for everything at once. And I think the efficiency of a monolithic approach is better in that sense, but eventually trump the monolithic approach. Okay. Yeah. I think it would. Yeah. In terms of accuracy, definitely. In terms of safety, probably not by a significant amount anytime soon. But in terms of accuracy, I think a modular ML approach is definitely the best. It's a good hybrid way of going about it because you still incorporate machine learning, but you solve each subproblem independently. So I think that's the approach that's going to win out in the long run. And I think monolithic approaches are more of an academic thing. What do I think the greatest barrier is currently to the future of self-driving slash driver of cars, attitudes towards it, technical limitations, and large enough data sets? Data sets is a big problem, but companies are getting into that. So Comet AI has a data set. Tesla AI has a data set. They're currently using them internally, but data sets they're accumulating, so that's not a problem. Technical limitations, like I said, yeah, that is a pretty big problem. I think one thing that you mentioned there, attitudes towards it, is a huge problem. So far there have been two fatalities caused by autonomous vehicles. One by an Uber vehicle that was level 4, and it was caused by a system failure. And really, it shouldn't have happened because the human driver should have been paying attention. But there was one Uber fatality and there was one Tesla fatality, and both of those received absolute huge amounts of press, and that really affects the speed of adoption of autonomous vehicles. So I think if we treat autonomous vehicle fatalities with less gravity, then we could improve the adoption by a lot. How do you apply color segmentation to a live video? From what I've seen, is really slow to be efficient. How do you apply segmentation? Lots of maths, computer vision algorithms, and sometimes object detection. Lots of it involves inference from colors, and it can be efficient, but it's difficult to get to a decent level of efficiency, I think. But yeah, I'd probably just refer to some further reading on segmentation uh, on video because I don't have a huge amount of experience with that myself. Any other questions? Yep. That concludes the self-driving car crash course part of it.